Hello everyone, my name is Felipe Gonzalez, and in this talk I'm going to present a new model based on ab initio simulations that aims to predict the temperature rise during RAM compression experiments. I am an assistant project scientist at the Department of Earth and Planetary Science of UC Berkeley, and in my research I use first principle molecular dynamics simulations to explore the properties of matter at extreme conditions. While these simulations have been able to reproduce and guide experiments in the past, it is unclear how to do it with RAM compression because a theory for RAM compression is still lacking. So, RAM compression is a dynamic compression technique that allows to compress materials to the extreme pressures present at the interior of exoplanets such as super-Earths. It is available at leading national laboratories such as the University of Rochester, LLE, and at Livermore National Lab. And the idea behind it is to design the laser pulse in such a way that the power is ramped up, like you can see in this figure. This design allows to compress the material without heating it as much as shock compressions do. The development of RAM compression is such that the compression path should be quasi-isentropic, meaning that it should closely follow an isentrope, where the temperatures are much lower than those reached in shock compression experiments. These conditions, isentropic conditions, are ideal to explore planetary interiors because planetary interiors that are assumed to be dominated by convection have an isentropic profile. But the problem with this is that there are currently no measurements of temperature in RAM compression experiments. There have been some estimates based on different models that only gives a range of possible pressure temperature conditions for these experiments, but there's no accurate theory that allows us to predict what the temperature is as the sample is RAM compressed. If we take a look at the RAM compression experiments of diamond in particular, we can find experiments that have taken diamond up to extreme stresses of 800 GPa, then to 5000 GPa, and then to 2000 GPa more recently. Unfortunately, the temperature measurements in these experiments were not possible, and temperature estimates were only available through models whose estimates have not been validated yet. Actually, it exists a large offset between the cold curve and the stress density data that cannot be explained by temperature only. So this leaves a lot of open questions for RAM compression. For example, what is the equation of state that we're using and what is the uncertainty on it? How are we modeling the strength effects and what is the role of plastic work? In particular, what is the thermal state along the RAM compression curve? What is the temperature at each of these stress density points? And finally, is the compression really isentropic? So in order to understand RAM compression better, let's go back to shock compression. In shock compression, we have a shock wave traveling through a material, leaving behind a new state of matter with higher pressure and temperature. These variables satisfy the Rankine-Hugoniot conditions that allows us to understand how these quantities are related. In fact, we can use ab initio molecular dynamics simulations to generate new equations of state for materials and solve these Rankine-Hugoniot equations. We do so by performing a number of simulations at given temperatures and densities, like you can see in this plot. And for each of these points, we can obtain the energy and pressure for those volumes and temperatures. And we can have a value for this H function here at each of these points. Then we can solve along a given isotherm when this function goes to 0, which is the point at which the Hugoniot conditions are satisfied. We have successfully done it in the past for several materials, in particular for magnesium oxide and for MgSiO3, where you can see here that our predicted shock-Hugoniot curve, here in black, agrees perfectly well with experiments at pressures that go even up to 3000 GPa. In the case of MgSio3, we also have very nice agreement for shock compression experiments that went up to 10,000 Kelvin in temperature. But the problem is that for RAM compression, we do not have equations like the Rankine-Hugoniot equations that allows us to predict from the equation of state what are the temperature and pressure conditions reached in RAM compression. And that's why we want to suggest the following model. So our model is based on the idea that RAM compression should be similar to a multi-shock compression. If we consider a material with a principal Hugoniot curve, where we take the material from ambient conditions to a final state of energy E, then this area that you see here that connects the 2 points and the Hugoniot curve is the heat generated for that particular shock. But if we're able to shock the material to an intermediate state and then from that state to the final state of energy E, we should be generating less heat compared to a single shock. So we think that RAM compression is like a series of shocks that come one after the other, and the energy goes into compressing the material instead of heating it. So what we will do in our model is to start from an initial condition in hydrostatic equilibrium, and we will perform uniaxial compressions as it happens with experiments. We will assume that this compression occurs isothermally because it's instantaneous, and the energy of this state, being less stable, will be always higher than the energy of an equivalent state with the same pressure and density. So this energy difference is actually the source which is energy stored used to heat up the material. So we will use this energy difference as kinetic energy to deduce what the temperature increase will be. So to summarize, our model workflow is the following. We start with an initial condition at density rho A and temperature TA, and we simultaneously compress both uniaxially and hydrostatically to a new density, such that we have two states at the same temperature and density. And then the energy difference between them is added to the kinetic energy of the sample, such that we get a new temperature as a result. So we start with an initial structure, perform both compressions at the same temperature, get the energy difference, and we heat up the hydrostatically compressed sample. Then the output of this simulation is used as the next step for our RAM compression model. So let's see how this looks like for 3 steps. We will go from ambient conditions to 800 GPa in 3 steps to 200, 800, and 800 GPa. So we should be generating less heat in total than going directly to 800 GPa. So this is how it looks like. We have our sample at ambient conditions that was uniaxially compressed to reach a new density that corresponds to 200 GPa. And then we calculate the energy difference with a state that has the same density and temperature but was isotropically compressed, and we put that energy difference as kinetic energy. And this results into a new temperature. Then this new state is used as an initial state for the next step, and the process is repeated until we reach 800 GPa. So you can see that the temperatures reached are actually much lower than the temperature along the Hugoniot, and this curve more or less resembles an isentrope. Let's have in mind that we do not force any of these states to satisfy the shock-Hugoniot conditions, but are just the result of this energy difference between the hydrostatically compressed state and the uniaxially compressed state. So how can we validate our model? Since there are no temperature measurements in the experiments yet, we decided to compare it with a multi-shock Hugoniot scheme. And the way this operates is the following. We used an equation of state for carbon that includes the diamond BC8 and simple cubic phases, And with this equation of state, we're able to solve the Rankine-Hugoniot equations, as I explained before, to obtain the principal Hugoniot curve for carbon. Then we use one point along the principal Hugoniot as initial conditions, and we solve the Rankine-Hugoniot equations again, generating a secondary Hugoniot curve. In the same way, we obtain a third, fourth, fifth Hugoniot, and so on, generating a multi-shock. Now, if we compare these multi-shock Hugoniot states with the model that I just presented, here's what we obtain. You can see that there's remarkable agreement between our model and the multi-shock Hugoniot scheme, where, once again, every point here is forced to satisfy the Rankine-Hugoniot conditions, while in our model there's no constraint on that. The temperatures are obtained just from these energy differences between the uniaxially compressed samples and the hydrostatically compressed sample. Our results also indicate that the sample remains in the solid phase, and temperatures are much lower than those predicted in a plastic work model by Bradley et al. We also compared our model with a recently proposed model by Swift et al., where they use the Taylor-Quinney factor, which accounts for how much plastic work goes into heating the system. And our calculations show that their model with a value of 0.25 agrees perfectly with our curve. This model was the same that was used by Amy Lasicki et al. In a recent paper where they reached 2000 gigapascals, but they were not able to distinguish which factor was more appropriate for the measurements they took. Now, there's still an issue reconciling experiments and simulations, and it has to do with this huge difference between the pressures along the cold curve and the stresses along the ramp compression path. So we decided to try several hypotheses, and the first one of them was to assume that the sample melted. So using our equation of state of liquid carbon, we assumed that the measured stresses were actually the hydrostatic pressure. And being the pressure a function of density and temperature, we can infer the temperature as a function of density and pressure. So doing so, we can infer what the temperature was along the ramp compression path, which you can see here in this figure in green. So, if the sample melted, we predict that the temperature reached in this experiment would have been so high that it could have been measured by pyrometry. In fact, it would have been between 20,000 Kelvin and 40,000 Kelvin. If we consider that at any given density the sample was solid and the pressure was hydrostatic, it turns out that no value of temperature is compatible with the reported stresses, because the sample melts before reaching such high values of stress. So we also tried with high strain values to see if the measurements were compatible with the equation of state of carbon, and we performed uniaxial compressions at constant density and temperature. So we just basically varied just the shape, and we found that even with strains beyond 12%, we are not able to reach the high values of stress reported by the experiments. We also tried incorporating 7.8% porosity like the experiments had, and it went the opposite way, where we were not able to increase the stresses in the compression direction as much as we could with the pure crystalline samples. And we finally tried to scale the density, because these experiments here were performed with porous diamond instead of pure crystalline diamond. So in order to take that into account, we basically rescaled the densities we had in our simulations for pure diamond. And we realized that only then this shaded area here, which correspond to the experiments corrected for initial porosity, agree with the model that we are proposing within the error bars. So we think that these experiments have to be revisited in order to explain this discrepancy between the predictions of the ab initio simulations and the measurements in the ramp compression experiments. To conclude, I would like to highlight that we have generated a model to predict temperature rise in ramp compression that is compatible with a multi-shock Hugoniot scheme, and also with a model that uses the Taylor-Queeny factor to account for the plastic work done in the system, and they are all consistent with each other. The discrepancies with the experiment has still to be explained by more experiments, but so far we account for the plastic work energies which are comparable with the energies predicted in our model between the hydrostatic states and uniaxial states. There's a possibility for non-equilibrium thermodynamics taking place in the fast ramp compression experiments, but those are still hypotheses that have to be tested. Thank you so much.